All right, so Kenshi, are you ready?
Yes.
Great. So it's my pleasure to introduce the first talk of the day. Kenshi Miyabe will speak to us about subclasses of the weakly computable reals. Go ahead.
Thank you very much. And thank you for the invitation. And thanks for coming to my talk. So I'd like to talk about subclasses of the weakly computable reals. And this is partly joint work with Kumabe sensei and Suzuki sensei. So main topic is real closed field. So we consider subclass of reals F, and the F is called real closed field. So if it is closed under addition and subtraction, multiplication and division, and taking real roots of polynomial with coefficients in F. So if two reals are given and it is closed under addition, so alpha plus beta is also in F, and alpha minus beta is also in F, and alpha times beta and alpha divided by beta. Such a thing is called the field. And we also require that, so it is closed under taking real roots. So consider the polynomials with coefficient in F. And so if the polynomial has a real root, then this real is also in F. Such a thing is called real closed field. So here are examples of real closed field. So of course, R itself is a real closed field. And well-known example is the real algebraic numbers. So it is the real roots of polynomials of rational coefficients. So it is real closed field. And classically, the class of all computable reals is also a real closed field. I don't know who is the first one to show this, but at least Poor and Richards in the book 1989 has a theorem of this. After that, so 7n and Leinov, I don't know how to say pronounce, but around the same age. So, and I think they are independently show that all weakly computer reals form a real closed field. I will say the definition of this later. And relatively recently, the mirror shows that all non-random weakly computable reals form a real closed field. This is an interesting result, I think. And further recently, I haven't read the proof, but so it is a closely related result. So they show that. So I think Ita-Hartring shows that in the primitive recursive reals form a real closed field. So it is in the paper by them. So the example of the real closed field. So today's goal is that, so I defined a new reducibility, strongly Solovay reducibility, and it shows that, so for each beta, this set, so strongly Solovay reducible to beta, the reals which strongly reduced to beta is the form the real closed field. So I try to explain why this is interesting or why how related to other notions and the known notions, known results. So for example, if beta is omega, so Chaitin is omega, and so this set, so the set of alpha such that alpha is strongly reduced to omega is actually so non-random weakly computable reals. So if beta is omega, this is just this result. But this theorem says that actually this is, so for any beta, this set is a real closed field. So, and this notion is a stronger notion of than Solovay reducibility, and it is not only for weak left-c reals, but also for the weakly computable reals. So I consider, so for weakly computable reals, we consider the Solovay strongly Solovay reducibility. And definition is this, but I will explain this later in more details. So from now on, so I'd like to review the definition and some related results. And first, I extend to reducibility. And I also talk about some related results, small results. So first, we review some definition and related results. So probably most of you know that, but just in case. So a real alpha is computable if there is a computable sequence of rationals such that the difference is less than or equal to 2 to the minus n, and alpha is the limit. So roughly, so n is the first convergent sequence to alpha. If there is a computable such sequence, then alpha is called computable. Alpha, real alpha is called weakly computable real. So it has a little weaker notion. So computability implies weakly computability. So if there is a computable sequence of rationals such that the sum of the differences is finite, this value need not be computable, but should be finite. Then, as a usual argument, so such a sequence always converge. And if alpha is the limit, then alpha is called weakly computable real. So of course, so if the difference is less than or equal to 2 to the minus n, the sum is finite. So computable real is weakly computable real, but not the converse. So some weakly computable real is not computable. Maybe this one is more familiar. So alpha is left-c.e if there is a computable sequence of rational such that the sequence is increasing and alpha is the limit. And it is known that the real is weakly computable if and only if it is difference of two left-c reals. So something like this. So alpha is weakly computable if there are two left-c real beta and gamma, and the alpha is the difference in this paper. So some people say that the weakly computable are sometimes called DC real or maybe left-c.e real. So these are reviews. And we consider the reducibility in weakly computable reals. So maybe it is more familiar. So Solovay reducibility for left-c real is more familiar to many of you. But here is a extended one. So alpha is extended Solovay reduced to beta, so denoted by the same notation. If there are a computable sequence n and bn of rationals such that the limit is alpha and beta respectively, and there exists C such that for all n, the difference is less than or equal to this value. So intuitively, Solovay reducibility means that if there is a good approximation of beta, so Bn is, if Bn is good approximation of beta, then you can compute a good approximation of alpha. So up to a multiplicative constant. So it is well known for left-c reals, but so here we consider weakly computable reals. So Bn may be larger than beta or maybe smaller than beta. So we need the absolute value of this. And so Bn may happen to be a very close to beta. So we need to some error constant, some error term, so 2 to the minus n. So if you delete this, so the reducibility doesn't work well, so does not perform well. So letting a chain show that this work well. So I use these definitions. So this is the extended Solovay reducibility. This notion is closely related to randomness. So roughly speaking, so difficult to approximate is the same as random. So a theorem says that so any matching with random real in weakly computable real is Solovay complete in weakly computable reals. So Solovay complete means so any weakly computable real is extended Solovay reducible to that matching with random real. So first, this notion, so for left-c reals for Solovay reducibility is studied by Chaitin, Solovay, and after that, so Galude and Kuchera and Suleiman show that so any left-c real is Solovay complete in left-c reals. It is a good result. And after that, Lettinger Chen, 2001, I think, any random weakly computable real is left-c.e or right-c.e. Further, so any weakly computable real is Solovay reduced to omega. So omega is actually top element in not only for left-c reals, but also for weakly computable reals. So these results imply any matching with random real is the top element. So only one degree, so Solovay degree, can contain matching with random. So picture is something like this. So these are the weakly computable reals, and the computable real is the bottom one, and this one is says that Solovay reducibility, and the top element is the only one degree that contains random real, and such real, it should be left c or right c. So omega or minus omega. Okay. So these are the reviews. Now I'd like to extend to these results to reducibilities. So first, so if let beta be a weakly computable real, then we consider this set. So a class of real of alpha such that alpha is Solovay reduced to beta. So of course, this Solovay reducibility is an extended one. And such set is real closed field. So this is one extension. Let me give some ingredient in the for the proof. So first, so this is the key observation. So local ellipsis functions in the proof. So f is called, so this is roughly a ellipsis function, but so locally, which means so for any real, there is a neighborhood u and in u. So already in u, okay. In u. So if restricted to the neighborhood, then in the neighborhood, so it is the function is ellipsis. And so we like to consider addition and division and so on. So we consider that the domain is to be R to the n. So with this definition, so this set is this one. This one is closed under a locally ellipsis computable function. So for example, if alpha is Solovay reduced to beta, then f alpha is also S reducible to beta. And not difficult to show that addition, subtraction, multiplication, division are locally ellipsis computable functions. And furthermore, so taking real roots of polynomial is also a locally ellipsis function. So combining these results show it is a real closed field. Actually, the Tinga chain already shown that, so this set is a field. A little after that, shortly after that, so McNichol showed that so implicit function of continuously differential computable function is computable. And with these results, so essentially one follows by following the line of the argument, you can show that it is a real closed field. So one thing we know. So of course, this is one subclass of weakly computable real, such that which is a real closed field. So okay. So I'd like to consider another extension. So mirror results means that so this one, so non-weakly computable non-random weakly computable reals forms a real closed field, which says that, so with another formulation is this. So alpha in weakly computable reals such that alpha is strictly less strict Solovay reducible to omega forms a real closed field. So roughly, this saying that, so one cannot construct a random real from non-random reals by taking real roots of polynomials with coefficients in the set. So it is natural to ask that, so can we replace omega with any weakly computable real beta? Unfortunately, this is impossible. Actually, for any non-random beta, this set is not a real closed field. This comes from the old results. So for example, so one is that, so the Meiji theorem says that if alpha and beta are left-c reals such that alpha plus beta is random, matching roof random, then at least one of alpha and beta is matching roof random. So taking contrapositive, if alpha and beta are both alpha and beta are not random, then alpha plus beta is not random. So this is a necessary condition such that so this set forms a real closed field. However, if beta is not random, this is not the case. So if alpha is non-random left-c real, then there are left-c reals beta and gamma such that beta and gamma are strictly below Solovay below alpha, such that beta plus gamma is equal to alpha, which means that this set is not a real closed field for any non-random real. So this violates the condition. So this is not a real closed field. So this is why I want to consider the strong Solovay reducibility. So first, we consider for strong Solovay reducibility for left-c reals. So I use this notation. I will explain the reason later. So alpha is strong Solovay reducible to beta if one of the following equivalent condition holds. So for any c, there exists a approximation an and to alpha and bn to beta such that this value is less than or less than this one. So if replace this for sum, then this means usual Solovay reducibility. And here is for any c. And not difficult to see that, so this is equivalent to c beta minus alpha is left-c real for any c. And c beta divided by alpha is left-c real for any c. So it's I think it's good to compare the equation in Miller's paper. So he defined the derivative of weakly computable real alpha at the limit of the ratio of the difference, and show that this is actually equivalent to this one. So if of C, that the C omega minus alpha is left-c.e. So in the paper, so this is so here is the right-c in converse, but so anyway, this one is equal to this one. And if alpha is matching random, this is positive, and alpha is not random, then this is 0. So I use the definition for Solovay, strong Solovay reducibility. So roughly this value is 0 for it, and replacing alpha with beta. And so for matching random real omega, then the convergence rate uniquely determined. So the ratio does not depend on the approximation. However, so in general, non-random reals, the convergence rate depends on the approximations. So that's why, so we cannot use this formulation, but if so this is equivalent to saying that, so there exists an and beta such that this one. Of course, this is equivalent to this one. So roughly means that so the limit is 0, but slightly different. So I use this formulation. So this one is strong Solovay reducibility. Then for left-c reals alpha beta, then we have this implication. This one is strong Solovay. This implies usual Solovay reducibility, and Solovay reducibility implies K reducibility. And actually, so this one, so strong K reducibility implies this reducibility, where strong K reducibility is defined by the Kolmogorov complexity up to n. The difference Kolmogorov complexity goes to infinity. So I like this implication because so 2 Solovay reducibility is sandwiched in 2K reducibility. And furthermore, this implication is strict, so this doesn't hold for the compass. So for the compasses do not hold. So for first one, so this one, so one can show that there exists a non-random left-c real alpha, such that so lim of the difference between this Kolmogorov complexity and this Kolmogorov complexity is finite. So since alpha is non-random, so alpha is strongly Solovay reduced to omega. But with this condition, strong K reducibility does not hold. So the first one does not converge. For the second one, so we already seen that, so just consider a non-random real beta such that alpha and alpha 2 is strictly Solovay below beta, and alpha plus 1 plus alpha 2 equal beta. So if both so alpha and alpha 2 is strictly Solovay reduced to beta, so this relation holds. But so if alpha is, so this set is a real closed field, so alpha plus alpha 2 cannot be, if so alpha 1 is strictly Solovay reduced to beta, then so if so alpha 1 is beta and alpha 2 is beta, then alpha 1 plus alpha 2 is beta. So this relation does not hold for this real. So this relation does not hold, this implication does not converse. So this is a notion between these reducibilities.
We have a question from the chat. Could you go back to this slide? Thank you. The question from the chat is, in the last part of the equation, what is alpha less than or equal to k beta?
Okay. So if for all n is a C, usual k reducibility. So roughly the complexity of alpha is less than or equal to the Coulomb complexity of beta up to n.
Well, thank you.
Yes. And this one. So with this definition, so strong Solovay reducibility implies that alpha plus beta is strongly Solovay reduced to gamma. So this is a necessary condition for a real closed field. And furthermore, if omega, so alpha is strict, so this is given to this way. So for beta is omega, then these notions are the same. But so if this one is non-random, beta is non-random, then this implies this, but not the converse. So now these are the 4 left-c reals. So let me extend to weakly computable reals. So this is a straightforward extension to weakly computable reals. So let alpha be beta be weakly computable reals. Then alpha is strongly Solovay reduced to beta. So this is also denoted by this. If for every C, there exists something like this. So if this one sum, then it is a usual Solovay reducibility, so extended Solovay reducibility. So just replacing sum for every positive C. Then it is not difficult to show that for any beta, so this set forms a real closed field. And so as you know, so this is equivalent to this is this. So if beta is omega, it is just a mirror result. And it is equivalent to mirror result. And just in case, so I'd like to introduce some properties. So this notion is Solovay degree invariant. So which means So if alpha 1 and alpha 2 are Solovay reducible, Solovay equivalent, and beta 1 and beta 2 are Solovay equivalent, and alpha 1 is strongly Solovay reduced to beta 1, then alpha 2 is also strongly reducible to beta 2. So this notion is Solovay degree invariant. And furthermore, for left-c layouts, the two definition coincide. For this means, so if alpha and beta are left-c layouts, this is equivalent to deleting this 2 to the minus n. So this definition. So this is an, I think, natural definition for weakly computable layouts. And actually, it is possible that alpha is strongly Solovay reduced to alpha itself. But so it is only the case alpha is computable. So of course, alpha is computable, then this holds. But if this holds, then alpha should be computable. So if for any non-computable alpha, this relation doesn't hold. So I think it's okay. So I already explained the main results, but I tried to introduce some related results. The first one is RK reducibility. So this result is by Ryknov. So if alpha is RK reduced to beta, means that Kolmogorov complexity of alpha up to n conditioned with beta up to n is up to bounded by a constant. Such relation is called RK reducibility. Then he showed that for any beta, this forms a real closed field. So I think this is the first one to show something is a real closed field with using some reducibility. But I think this is not the class of weakly computable reals, even if beta is weakly computable real. So I think it is a good result, but but it's not a subclass of weakly computable reals. I think more interesting thing is K triviality. So also this, the class of K trivial reals is subclass of weakly computable reals and form a real closed field. So this fact is somewhat straightly, somewhat immediately follows from these results. So Stefan Wu showed that there is a universal machine U and integer M, such that for any K trivial real R between 0 and 2 to the minus M, so very small one, such that there is a cos-CE set X with R is the halting probability of U restricted in X, which means UP, the output is, you enumerate the value only if the output is in X. So X is cos-CE set. So you enumerate this value, adding up. But after that, one knows that, oh, sorry, this value is nothing, X. So you need to decrease this value. But the sum of adding up and sum of decrease values are bounded by 1. So this value is weakly computable real. And furthermore, so weakly computable real and the k-triviality does not affect by changing the initial segments. So actually, this shows that k-triviality is weakly computable real. And probably this is well known that, so Daniel Hashbeth, Nice, and Stefan show that, so alpha, beta, if k-trivial, so it's alpha plus beta is beta. So alpha plus beta is k-trivial. So probably it is well known. So this is a necessary condition for real closed field. And essentially the same arguments show that, so k-trivial, the class of k-trivial forms a real closed field. So I think it is good to know. So this is another so independent interest. So we already seen that, so strongly k-reducibility implies strong Solovay reducibility and Solovay reducibility. But actually, so between these, there are some options for the definition, something like this. So k-reducibility, so for left-c reals, so k-reducibility, strong k-reducibility implies that for all, and this one is weaker than exist. So that's why, so there are some other possibilities for the combination of for all and exist, and of course the order Bn and An. So another question is that can we extend to these relations for weakly computable reals? So this is a straightforward extension is impossible. This is because there are alpha and beta. Beta is left-c and alpha is weakly computable real, such that alpha is so strongly k-reducible to beta, but alpha is this is usual Solovay reducibility. So usual extended Solovay reducibility. So alpha is not Solovay reducible to beta. The proof is something like this. So consider the half omega, and so this has the effective Hasse dimension 1/2, and this implies that the number of changes of beta, so this one can be bounded. So from which, so we can construct alpha weakly computable real. Alpha is k-reducible to beta, but not Solovay reducible to this one. So these implication only for left-c reals. So one cannot extend to weakly computable reals. However, so why we can imply so from this to this? This is because the key observation for the proof is that roughly these are the same complexity. So if given the initial segments up to n of alpha, then one can compute the stage that the difference is 2 to the minus n. So we can say that the when is sufficiently close. And of course, alpha is left-c.e. So this is roughly the same as max S, such that this one. So if beta converges faster than alpha, then one can compute the initial segment of beta from that of alpha. But this argument doesn't work for weakly computable reals, because weakly computable reals, at some stage, so AS is very close to alpha, but after that, AS is relatively far from alpha, and after that again, so AS is very close to alpha. So with this observation, so I use monotonically computable reals. So Rettinger defined this notion. So alpha is k monotonically computable if there exists approximation such that this one. So this relation says that so if an is sufficiently close to alpha, then after the stage, so the stage after n, so the difference is bounded by the k times this one. So roughly says that if once close to an, then so an cannot be far from alpha after the stage. So you can, so the convergence is not monotone, but roughly monotone. Then if, and alpha is called monotonically computable if it is k monotonically computable for some k. Then with this definition, so alpha is 1 MC if and only if it is left-c.e or right-c.e. So this is kind of an extension of left-c.e. And furthermore, any monotonically computable real is weakly computable real. So this is a subclass of weakly computable reals. And this is the interesting result. So if C1 and C2, C1 is larger than C2, then there exists a C1 monotonically computable, but not C2 monotonically computable. So monotonical computability has a hierarchy of this C1, C2. So this can be any Q, so any rational. So need not to be an integer. So with this definition, so one can show that so for any monotonically computable reals alpha and beta, then strong K reducibility implies strong Solovay reducibility. This is a slight extension of the this implication for left-c.e. reals, but anyway, we can show this relation for monotonically computable reals. Okay, that's end of my talk. Thank you for attention.
Thank you. Are there any questions?
Yeah, hi Kenshi. Can you say maybe something about your proof that you have a non-random real whose Kolmogorov complexity doesn't diverge away from omega?
Oh,
That's a bit surprising, let's say.
this one.
Yeah. How does that go?
I use some results by actually I didn't construct so I think Lian constructed a real for some other property, and actually the same witness also has the property, this property. So that is why, so we know that this Liao exists. So I do not know the
Sure. Otherwise, it would be
detail-
random.
detailed construction, but yes, but so we need some reference.
Thank you.
Any other questions? Check on Zoom. So I have one question, which is,
Yep.
So you've given a number of examples of real closed fields that are subfields of the weakly computable reals. And I suppose there could be many of those probably arranged in some structure by subsets. And I was wondering if you could say something, if you have thought at all about the structure of the collection of all weakly closed subfields of the weakly computable reals arranged by subset.
I don't have so knowledge to answer the question. Sorry.
Okay, thank you. Any other questions? All right, so let's thank Kenshi again. Thank you so much.
Thank you.